to do another version of how Mother Nature does opacity and transparency. I mentioned three ways that Mother Nature deals with opacity and transparency, the opaque and the transparent. And one of them, the way she does it, is with alignment. That's my argument, okay? I'm saying that one of the ways she does it is with alignment. And what I showed was that, we took a couple lenses. They were these polarized lenses. And if you can see there, you can see that light disappears when at the end of the black screen there, when the lenses are perpendicular to each other. But when they're parallel, the light goes through. So it's transparent in one direction, but when the molecules are rotated, it's no longer transparent. Now it's opaque. Okay, so if you were at the other end of that laser, the laser pointing to your eye, you would see it when the two lenses are parallel. But when they're perpendicular, the light does not reach your eye. Okay, and that's what I'm showing there. I'm saying that the molecules, okay, calcium carbonate, when they're rotated, they're now misaligned. Okay, and one of the ways you can do that is that way, which is the ropes that were connected from one atom to the other straight ahead are no longer, in a parallel direction to the a laser or the beam that's coming in there. Okay. The other way I suggested is that by rotating, what you're doing is twisting the rope. Okay, and by twisting it 90 degrees, okay, you're actually changing the link lengths, okay, by a certain amount, an amount enough to take it out of the visible range. Okay, that's why it becomes opaque or transparent. And one fellow questioned that, okay, it's good to have people question it, says when you rotate the lens 90 degrees, the rope also rotates. Would that not then imply that if you were spinning the lens with a motor, you would rotate the rope more and more, thus changing the frequency of any light entering those molecules, okay? Is it not more likely that the turning of the lens 90 degrees would not change the link lengths because the whole electron shell, in fact, is like a slippery ball that spins to keep the ropes at the same orientation, much like a bubble, okay? Good input, and I'm not going to give him an answer yet. I want to continue, okay? Let me continue, and maybe we can find the answer he's looking for, okay? One fellow says, explain transparency in materials where the atoms are not aligned, like in the water. The water is transparent whether still or in motion. You know that water molecules are constantly in motion, don't you? Do you lose transparency just for a moment when the molecules move? You say that the alignment is not the only mechanism that explains the transparency, and then you spend several minutes explaining water transparency by the alignment of water molecules. Okay, so let's address both gentlemen here, okay? Kill two birds with one stone. First of all, nowhere did I say, the first person is just suggesting, the second one is stating, oh, you said this. No, the reason he said this, mentioned that comment, is that he wasn't paying attention when I was talking. He was busy talking himself. And so, when you talk and you don't listen, well, yeah, you're not going to understand what's going on here. What's going on here is I'm not here to give you answers. Okay, I'm not here to give you answers. I'm here to provide you with the tools necessary for you to figure it out on your own. If you go back to the ancient Greece, right? You had Socrates, and allegedly he got together with his pupils, his students, and he never wrote anything. And again, it's the victors who usually write history. In this case, he wasn't a victor because he was forced to drink hemlock. But his students wrote about him, and we can only go by what they tell us. Among them, Plato and Xenophon. Later on, a student of Plato, Aristotle, he also mentioned them, Socrates. And the way apparently Socrates dealt with his students was when they asked the question, he would typically answer with another question. And it's a good method because it throws the ball back to the student, and the student now has to think. If you just give him the answer and say, this is the answer, so, oh, okay, I'll memorize that for the test. And so he hasn't really grasped what you were telling him because it was a freebie. So he said, oh, okay, I see what you're saying. And he didn't see anything. And so the issue here is, I'm not here to tell you how transparency and opacity is done. I'm here to give you clues of how Mother Nature does transparency here in this situation, in this situation, in this other situation. And I'm showing you that also, parallel to that, that you cannot explain those situations, transparency, opacity, with waves or particles, quantum. You cannot explain, you cannot give a physical interpretation to opacity and transparency using the waves and particles of mathematical physics. That's where the problem is. And so I'm contrasting the rope model against that, and I'm showing you that under the rope, you have all these options. One of them, like I'm saying, is twisting the rope. The other one is the rope itself goes out of alignment because, you suddenly, move that thing around. And so now the light from the laser does not go through the same ropes to reach that first the second slab and then the screen. I'm just giving you clues. You're supposed to give me the answer. Okay? And nowhere did I say, hopefully I didn't say, that either air or water or glass is because of alignment. Okay? I'm giving you an example of something to keep in mind when you're looking at all these transparent media. Okay? And so people confuse that and say, oh, Bill said. No, I didn't say anything. I didn't say how, why. So far I haven't said, as far as I know, so far I haven't said why air, water, or glass are transparent. Okay? I'm giving you clues, what to reject, what to accept. Okay? So you're supposed to figure out why air, water, and glass are transparent and brick walls are not. Okay? Second issue, I said, well, one is alignment, one thing to keep in mind. I did say, by the way, yes, I did say that in the case of polarizers, it is the 90-degree turning of the molecules. Okay? That I did say. It's the only one I said so far. Okay? Other than that, I haven't talked about air, water, or glass. I'm not telling you why they're transparent. I'm suggesting you look at the fact that even though, like this fellow says, water moves, air moves, the question is, when you rotate water, does the molecule rotate as well, or does the water remain in the same direction with respect to the center of the earth? Gravity, in other words. That's the issue. Okay? For you to ponder. Do the molecules of water stand under side, oxygen, hydrogen, oxygen, hydrogen? If they're like that, do they also stand like that, despite that the water level, you can see that the water, when you turn that glass around, the water stands still, more or less. It moves a little bit, but water remains level with respect to the center of the earth. Gravity does play a role in water for some reason. Does it play a role inside a balloon full of air? Does the air also turn on its side, the double O, oxygen, or the nitrogen that's in there, whatever's in there? Does it turn on its side, or does it remain always in the same direction with respect to the center of the earth? I'm trying to give you clues to get you to think. Okay, let's see if that sinks in. Okay, we did quantity, and here we put a single sheet, and the sheet looked like this. Okay, just a little plastic. Here it is. Okay, you can see it's just a little plastic. Okay, very thin sheet. And when I put many sheets, okay, you can see the light from the candle doesn't show through. So quantity is also important. Apparently, Mother Nature, if she has a very thin sheet of something, she may allow light to go through. But when she has many sheets of whatever, many of those, then light does not go through. So she built opacity with many transparencies. Okay? Second clue. It's a clue. Okay? Did I say, is that the reason water, air, or glass is transparent? I haven't said anything. Okay? So I haven't said that. Okay? Okay, so where do we go from here? Well, a couple people had problems with that. Okay, and let's see what they have. Here's the first one. Fellow says, of course you know that when light is equal on both sides, it appears as a mirror, but you can also see through to the other side. He's talking about, one-way mirrors. Okay, you can see yourself in a mirror, and the person on the other side can see you. And how can that possibly be? Here we have you think it's a mirror, and for the other guy, it's a glass. It's a transparent glass. He can see you, and you can't see him. Okay? And so he's saying when light is equal on both sides, it appears as a mirror, but you can also see through to the other side. Okay. Thank God someone mentioned that. We didn't know that. Okay, and here's another fella. See if I can get him here. Give me a second. And he says the same thing. He says, polarized lenses are coded. A one-way mirror works similar to polarization. A mirror has aluminum one side of the glass, and we can see through it. The one-way mirror has to have the lighting double the brightness on one side for the illusion to work. So neither of these two fellows paid any attention at all whatsoever to what I said. Okay? They think it's got to do something with lighting, and the one-way mirror has to do with lighting in the room. Okay? It has nothing to do with the question, with the issue that I addressed. So they're barking up a tree. They're beating up a scarecrow, dragging him through the mud, because they're not addressing the issue. Let's see if they can understand the issue, what the issue is. I don't think they will. They probably don't have the capacity to understand this. Okay, so let's go slowly, at least for the mentally disadvantaged people who come here. Okay, let's get rid of all the lighting. Okay, you want to put the lighting, put the lighting. I don't care. It's irrelevant to the question at hand. Okay, with the issue that I'm going to be addressing now. Okay, we have a laser pointed from one direction, and we know that the laser goes through. The light from the laser, the photons of the laser, not of the room, but of the laser. Okay, so the photons that make up that laser beam, that ray, those are going through. Okay, because I can see the laser from the other side. I can see everything in the room from the other side. But it turns out the person on this side cannot see the laser, the photons coming out of my laser that are going through, and instead of bouncing, because it's a glass again, but it's the same glass for both of us, right? Mine don't go through. Mine, I'm sorry, he can't see, the guy on the other side of the mirror, he can't see my laser, but I can see his. And the first question is the material that make up that mirror, this one-way mirror, is it the same in either direction? Has the amount of material, has the amount of molecules, atoms changed? Why am I bringing this up? I'm bringing this up because the explanation that quantum mechanics gives to this phenomenon has nothing to do with lighting in the room. Okay, let's see if you understand this. The quantum explanation has nothing to do with lighting in the room. It has to do with whether an electron of that material that you see there, of the glass, coated or uncoated, I don't care, whether the material absorbs a photon. It's the same material in either direction. Okay? It's got coating on one side, doesn't on the other side, I don't care. It's irrelevant. The material is the same. In other words, the material that the rays of the photons have to pass through is the same either way. Do we understand that or not? Has it sunk in? It's the same material. So the question is, why does the electron of one of those atoms that builds that glass, that coated glass, why does it accept this photon and does not allow it to go through? And why does it, in the opposite direction, does not accept that photon? The photon's supposed to kick the electron to a higher energy level, right? It doesn't do that, and so it goes by and you can see it. It's the same material in either direction. So we're addressing quantum mechanics here. Forget about your lighting. It's nonsense. It has nothing to do with the question at hand. Okay? So here's what I showed. Maybe they watch it, I don't know. This is how quantum mechanics explains both, this serves for both cases, for transparency and opacity. What are we staring at here? We see a little photon. It hits the electron, which is at a lower energy level, and it knocks it into a higher energy level. We say that the electron absorbed the photon. When it does that, the photon doesn't get through. Okay? On the other hand, if the if the photon doesn't come with sufficient energy and doesn't kick it to the electron to a higher energy level, then it goes by, it zips by, and that's when you can see it. That's when the material is transparent, according to quantum mechanics. Okay? So again, if the material, the only thing that blocks the rays of light in either direction, okay, if the material is the same, why would it absorb the photon in one direction and not absorb it in the other? That is the question. Okay? So don't talk about lighting, it has nothing, or coding, it has nothing to do with the question at hand. Okay, let's see if we can continue. And again, it's because these people don't listen. They're not paying attention. They just want to say what they learned in college, what they memorized in college. Oh, but it's got coding. Oh, but the lighting in the room. They're not listening. Okay, temperature. I said that's another factor we got to consider when we look at transparency and opacity. Okay, and what I did, I took a glass and I put a pen in there and froze it, and then I just let it outside, let it melt, the ice, and I filmed it every 10, 15, 20 minutes. And there you can see what happens suddenly, the pen comes into view. It was not visible when the ice was solid, and it's visible when the ice melted. So temperature did something. Okay, apparently temperature has some bearing on opacity. That was my argument. Okay, and you can see something similar at the bottom where you see a pot boiling. You have that water come out as steam, and it's hot. And apparently the temperature did something to the water, because the water inside that pot would be transparent, but the one there with all that smoke coming out, that's not transparent. It's that foggy thing. So temperature apparently has something, okay, to do with transparency and opacity. Okay. Did I say that water is transparent because of heat? No. I'm giving you clues. All the things you got to factor when you ponder why something is opaque or transparent. That's what I'm saying. I'm giving you tools. Okay, please understand the situation here. Okay, okay, and here we continue. The fellow says, you better not use water becoming opaque when it freezes in the next video, because those are air bubbles reflecting and scattering. It's almost easy to make ice as clear as liquid water and not hard to find pictures of it online. Okay, so he's saying that ice and water are both completely transparent, identically transparent, and that my experiment really did not prove anything or show anything or whatever, to him at least, because he said what I did was trap bubbles. In other words, that water had more air, I guess you could say, more air than water, and that by capturing all those bubbles, that's what made the water opaque. Okay. Well, it could be. I'm almost sure that's the case, but I just want to show you something, okay, for you to reach your own conclusions again. Here's different pictures of ice that, like the fellow said, you can find a lot of pictures of ice out there, and I haven't seen that they are very clear as water. The other thing I want to mention, if you look at all these pictures out there, okay, and if you Google them, you'll find that they all have to do with commercials. There are companies who are trying to sell you a machine that makes ice. And so they'll say, look, our machine makes great ice, and if you put this ice and you do it this way and this way and that way, you'll get clear ice, pure ice, and it's crystal clear. So they're giving you a sales pitch, and that's what most of these pictures are all about. They're about, selling. Have they done anything very, like a lot of people say, scientifically? In other words, did they do a controlled experiment? And the answer is probably not. Okay, they just say, look, if you boil water, get rid of the gas, the air bubbles, then you're gonna, and you freeze that, then you're gonna have a better chance of having crystal clear ice. Okay, but if you look at some of the pictures out there, the jury's still out for me. Okay, you look at clear ice, and it doesn't look so clear to me. Okay, and that's just one picture I pulled out at random. Okay, here's another one. I just want you to look at these pictures. Okay. In comparison against water. And I don't know, I still say that ice, even if you do it perfectly well, get rid of all the air bubbles, whatever, nitrogen, whatever is in there, okay, I'm not sure you're going to get it as crystal clear as water. Pure water versus pure ice, I think that ice is a tiny, itsy bitsy, more opaque than water, okay? Okay, so you don't believe me. Don't believe me. Don't accept what I just said. Let's go further. I did mention this, and that's argon is solid. It's more or less transparent. Liquid, it's also more or less transparent. In a gaseous state, the opposite, okay? In a gaseous state, heated, right, at room temperature, it's opaque. So here we have the opposite effect, okay? We went here, in the other case, we went from liquid to solid. Here we go from solid to liquid to gaseous, and it becomes opaque in that direction. Okay, so my argument was what? Temperature has something to do with opacity. That was my sole argument. Did I say that water is opaque because of heat? Did I say that air is transparent because of heat? No, I'm just giving you the tools to look at all the factors that govern transparency and opacity. Okay, so let's keep the context in the right place. Okay, so again, one of the issues here is that I'm not here to give you answers. Okay, I try not to give you answers if I can help it. I'm trying to get you to think. Like Socrates, you ask a question, I'm going to try to give you clues and ask you a question. I think it's better. It's more healthy for your state of mind. Okay, it makes you think. Means you understood what I'm saying. If I just give you the answers, oh, okay, Bill said this, and walk away, you never understood anything. Okay, that's one of the points. The other point is that I'm trying to make is, we got to destroy quantum mechanics, the nonsense of mathematical physics, which still 400 years later is still doing all simulations with particles and waves. Okay, and so one fellow asks, he says, light is passing through glass. He insists that light travels through. And so, yeah, that's a statement. You haven't said anything because you haven't told us what it is that is traveling through the glass. Okay, are we talking about particles? Are we talking about waves? Are we talking about ghosts? What's going through the glass? You have to identify the object. If you haven't identified the object, you cannot say travel through, passing through, goes through. You cannot use that term because you haven't identified the object yet. Okay, so you need to identify the physical object that is going through the glass. Okay, then you can say, yeah, see, I can show you a movie of how whatever, a particle goes through the glass, or how a wave goes through a glass. And then, of course, you got to identify that object. And of course, we know there's no such thing as a wave, because a wave is a bunch of vectors. Particle of quantum is a concept that's a zero-dimensional point particle, meaning it's a wave function collapse, which is a concept, and we don't move concepts in physics. So we have no particles and we have no waves. So you can't use the particle or the wave. So what is the physical object that's going through the glass, traveling through the glass, breaking through it, and it doesn't break it? You have this photon going through there, all these bullets, and they don't break the glass? Okay. And so a fellow insists, he said, wave is both a noun and a verb, light. Wave has peak and trough, width and height, width and length. We can see and touch with human perception. You can touch a wave. Wave is an object. Oh. Well, again, all we're seeing there are vectors. What's a vector? It's magnitude and direction. And what these people are saying is that we have magnitudes that are traveling. We have number 5s that are traveling, number 6s that are traveling. That's what they're saying. So no, 5s, 6s, 7s, and 8s don't travel. You have to identify the physical object that is traveling, that is waving. Okay? And they, a lot of these people say, well, we have the math, we have the equations to show you that we've measured, and we've put the observation in the form of an equation, so we describe what's happening in there. Well, can an equation tell you what physical entity, what invisible, untouchable entity is doing light, is doing gravity, is doing magnetism? You have the equation, and here's the equation, okay? You have an equation, and it shows a rabbit that is moving, okay? Well, maybe that's what your equation says, but maybe what's happening is something else. Maybe it's a snake that's twirling in place. Maybe that's what the invisible thing is. So maybe your equation is, for that invisible entity, is wrong in the sense that you think there's something moving from A to B, from left to right, and what's actually happening is something is twirling locally in place. In fact, that's what a wave is. Okay, so the question is, is the equation going to tell you what invisible entity you're mapping, representing with that equation? Okay, so you have to know what the object is, and for that, there is no other way. You can't go to the lab because you're not going to be able to see or touch it, because by definition, it's invisible, intangible. That's the description, okay? So you're not going to be able to go to the lab and use your eyes or your hands to see that which is invisible or touch that is intangible. The only way is to drink a beer, go back, and and think. This is something you have to try to visualize. You visualize first, then you're going to apply the equation. That's the way it works in science. If you want to describe it with an equation, go ahead. But right now, what we need is a physical object. And right now, we don't have a physical object coming from the mathematical establishment. But all those people who talk about, traveling through, that's what they got to come up with. They have to come up with the object that is traveling through, going through, moving through. Okay? We want to know what is it that is moving. Okay, because for all we know, maybe all you're doing is describing the humps of a camel that are moving up and down locally. Okay, so what's the fourth one? We had alignment, we have the quantity of material, right, the different layers, and we have the temperature. Okay, so we have 3 clues now that Mother Nature uses to govern opacity and transparency. Today, let's look at crystal structure. Okay, here we have transparent. Generally, we have gases or liquids. Not all of them, but a lot of them are transparent. And in general, we associate what is opaque, opacity. We usually associate that with stiff things, with rigid material. Okay, we think of a brick wall and we say, well, that's not transparent. We think of a steel beam, we say, well, that's not transparent. So if someone asks you to name things that are transparent, you would say, well, air, water, glass. You name the usual suspects. Okay, you don't mention those things which are generally solid. Okay, of course you have tables which are transparent and so on. Glass more or less looks solid, right? You can touch it; it's quite solid. But in general, we associate transparency with malleable or soft things, whereas hard things are typically opaque. Okay, and so I want to address that today and just give you this other clue, fourth clue. Okay, and here's one way of looking at it. I want to show you this. I do it with a ball and I throw it against a spring. Okay, and the spring is pushover. You know, you can push a spring almost anywhere you want. The spring itself is malleable; it deforms. Okay. So you would think that if light behaves like that, right, the spring would pass whatever motion is given to it to whatever's behind it. It would, you know, send that same signal behind it, meaning that maybe it's a way that Mother Nature does transparency. In other words, imagine the rope giving a signal to that spring, and the spring is such a pushover that it just gives a signal to whatever's behind it. Okay. On the other hand, you know, if you do it with a tree, right? Well, you know, the ball doesn't the tree doesn't really pass it on, that vibration, to whatever's behind it. Okay, it does receive a little vibration, a tiny bit, right? But the point is that it's not going to move the world behind it. And so I'm saying that maybe this transparency, opacity, has something to do with the rigidity of the molecules that form whatever body you're analyzing. Okay, but there's a problem with that. Okay, and let me show you what the problem is so that you balance that on the other side again. How about sound? You know, you have sound, you make a noise, and it travels through the air. But it turns out that sound travels faster in liquids and even faster in solids. So you would think that if I send sound waves, meaning that I'm not sending any wave, meaning it vibrates locally, right? If I send these sound waves, just to speak like that, okay, I'm going to use that language, you would think that if a solid thing transfers that sound faster, you would think that that would be the means for transparency for light, and it would be the other way around. In other words, it would be solid things, rigid things, which would be transparent, like steel and walls, brick walls, and not air and water, because again, they're pushovers, and maybe if sound is a good analogy for light, maybe it works the other way around. Okay, so maybe that kind of balances it out. You can have arguments on both sides on that. Now, it's important to understand that sound, you know, is built with molecules. Molecules are vibrating in situ. Okay, and I showed that the other day. Okay, and first here we see solids versus liquid and gas. You can see that sound travels faster in solids than in liquids, and liquids faster than in gases. Okay. So, and it's due to the density of the molecules that build up those materials. Okay, so that's one thing to ponder. But here we see that, you know, the waves are local. In other words, when I talk, the molecule that I'm vibrating here in the air, that's not the one that reaches your ear. And even in a steel beam, if I send sound through a steel beam, the molecule that I vibrate at the beginning of the steel beam is not going all the way through the steel beam to your ear at the other end. Okay, it more or less works like this. Everything vibrates in place, and you receive the final vibration from the atoms, molecules that are close to your ear. Okay, which again vibrates the air that's close to your ear. Okay, so the issue is there's no traveling through. That's the main point. Okay. This notion of traveling through first has to die. But then the question is if sound is a good analogy for light. You have to remember Huygens, you know, Christian Huygens, when he simulated light, he used water waves as an analogy. He said, what if we drop a stone in the water and we create these waves, and maybe light is like these water waves? Well, obviously he was wrong, you know, but I mean, it was a good first attempt, no problem there. But it turned out that that's not the way light behaves. And so the question is, can we use sound as a simulator for light as well. And the first thing I have to point out is that in space, sound doesn't work. Okay? Now this is important for several reasons. The first one is that light does work in space. Light goes from the Andromeda galaxy through space, we'll use that, traveling through space. Somehow light reaches us from the Andromeda galaxy. So space does not seem to be an impediment for light. On the other hand, sound does not travel from one astronaut to the other through the space right here in our solar system. You know, they're both on the moon, which is what, 10 to the minus 11 torr. Very few molecules in that at that level. And so an astronaut would not be able to talk, even if he took his thing off and he could talk, right? He would not be able to talk to the other person, or the other person would not be able to hear him, because there's nothing to carry, to use that term, the sound waves. There's no material to vibrate locally, as you just saw. Okay, light goes through, sound does not go through space. Okay? And so if that's the case, here let me show you an example here. If space is made out of particles, as quantum mechanics holds, as mathematical physics holds, they say that space itself is made out of particles. And if that's the case, then why is it that light goes through? You could say, well, yeah, because it's made out of particles. How come sound doesn't go through if those particles are there? If all of space is made out of particles, why don't they vibrate when we talk through space? Okay, we have a problem there because they use space. They say space is made out of particles, but those particles do not carry sound. Well, why not? I mean, why don't they wave when sound goes through there? And some people say, well, Bill, you're wrong. You got it wrong. No one ever said that space is made out of particles. Okay, so let's prove them wrong. Let's prove these people wrong so that they never open their mouth again. Okay, let's show them what quantum says. Okay, because they don't know their own religion. Okay, the quantum the first part is from the Wikipedia. The other is from another website, but you can look it up anywhere you want. Just look up, for example, pair production. And you'll find out that, yes, quantum says that space is made out of particles. The Dirac space is made out of particles. They're all saying the same thing. They've been saying it for 100 years. So if you haven't been listening, that's your problem. Okay? The quantum vacuum or quantum state is the quantum state with, or vacuum state is the quantum state with the lowest possible what energy, whatever energy is. What is it, a concept? Okay, you might say, well, energy is a concept. So what do they say? They say the space is made out of concepts? Quantum foam, also known as space-time foam or space-time bubble, is the quantum fluctuation of space-time. What is space-time? A concept, right? What is time? Isn't time a concept? Okay, they're talking about the fluctuation of time. You know, it's fluctuating, it's moving, it's vibrating. Time itself. The second is moving up and down, 5 seconds. Okay, on very small scales due to quantum mechanics, matter and antimatter is constantly created and destroyed. I don't know what destroyed means because they blend and they form what? Nothing? Two particles get together, they form nothing, and then they come out of nothing and form two particles? They're just cheating. They're saying that a black particle and a white particle form a no particle, and the no particle can separate into white and black particle. What they're really saying is, well, we don't want to call that one in the center a particle. And so they say it disappears, whatever that means. What does disappear mean? What did the particles turn into? They turned into nothing. What is nothing? Please define the word nothing. What is it, a particle? Is it a ball? Or what does nothing look like? Okay, so the issue here is these people are cheating because they're saying we have two balls, they get together and they form a no ball. And they say a no ball, but they don't define what a no ball is. In other words, nothing. And then they say from the no ball, from nothing, suddenly two particles, two balls come out of there. It's cheating. Of course, Feynman says nobody understands quantum mechanics. How can you understand if you're giving me an irrational explanation and trying to get away with it? Okay? A vacuum is defined as a space with as little energy in it as possible. Always that word energy, it fills all the blanks. Despite the name, the vacuum still has what? Quantum fields. Fields, what is a field? A concept. Numbers, that's what a field is. A bunch of numbers, that's all it is. Potential at each point in space, that's a concept. According to quantum mechanics, particle pairs are constantly appearing and disappearing as a quantum foam. Okay, so is the vacuum made out of particles? Of course it is. They just don't say it that way, and that's why you missed it, but that's what they're saying. And this other side says pair production is the opposite of annihilation. So we have annihilation, two particles form, annihilate, whatever, they turn into zip, and then zip, whatever zip is, turns into two particles. Well, I have to believe that zip is a particle itself. What is zip? What is this nothing? Is it a ball? Two particles turn into one ball? What is this zip? Unless you define that, you haven't said anything. Okay? Mysteriously, particles can appear from nowhere. Yeah, that's called magic. It's not called science, it's called magic, black magic. Okay, so yeah, first of all, quantum does say, mathematical physics does say, general relativity does say that the vacuum space is made out of particles. Space-time warpage, what is warping? A whole bunch of particles. A point at each, an event is a point in space-time. What is that point? It's a thing. That's what they insinuate. Okay, so the physical interpretation is that, yeah, space is made out of particles. Okay, until you understand that, you haven't understood anything of mathematical physics, of quantum mechanics, of general relativity. So get that through your thick skull. Space is made out of particles according to quantum mechanics, according to mathematical physics. But then, if that's the case, why does light, which is the vibration of all that ether, right? Why doesn't sound do the same thing? If space is made out of particles, why don't those particles vibrate and I can hear sound through space? See, that's when they introduce the vacuum, the space, and they say, well, there's nothing there, and that's why you need molecules in there. Why do I need molecules? Can't I do with the particles of space? That's the question. Okay, so what are the conclusions today? Well, we have 4 variables now, okay, for you to ponder, okay, when analyzing transparency and opacity under the rope model of light, okay? Alignment, quantity, temperature, and today we have molecular structure. I'm saying that if rigidity has something to do with, in general, okay, with how light is, whether the material is transparent or not, okay? Opaque. And what is this whole thing all about? Well, it's got nothing to do with me saying that water is transparent because the molecules are aligned. Never said that, never will, okay? Don't ask what Bill can do for you, ask what you can do for Bill. Don't ask, tell. Your job is to tell me how, or tell yourself. You don't have to tell me necessarily. I'm not your confessor. Figure out by yourself, using these clues, why glass, water, air are transparent and a brick wall is not. I'm giving you the clues, the tools for you to figure it out. Okay? That's the context.